All right, welcome to our Unit 7 quiz review. We got our quiz coming up, and here's everything that you're going to need to know for it. Let's start with number one. Number one says, during his NBA career, Larry Bird made approximately 94% of all free throws. Suppose Larry makes 10 free throws in a row. What is the probability he will make the next free throw? Can't overthink this one. This is just simply going to be 94%. 94% because, well, he's a 94% free throw shooter. And probability does not change. Okay, doesn't change. So remember that. It's a pretty simple one. Don't overthink it. It's not like, oh, he's made 10 in a row. No mathematical equation here, right? He's made 10 in a row. Maybe he's gonna be less likely to make a 10. He's 94, 1 out of 11. No, I don't. Nothing like that. Just it's 94% no matter what, right? Those are his odds every single time, regardless of how many he's made or how many he's missed already. And recently, long term is 94%. So odds are 94%. Number two, a statistics teacher states the probability of a surprise quiz on any given day is 60% or 0.60. If quizzes are given independently of the day, what is the probability there will be a surprise quiz on the next 2 consecutive days? Well, there's a independent clause here, which states, hey, if it's kind of like think of it like flipping a coin, right? If you were to flip a coin, right, there's a 50% chance of landing on heads. But if you flip it twice and you have a 50% chance of landing on heads again, then you have a 50% chance the first time and a 50% chance the second time of it being heads and heads, which combines to be a 1 in 4 chance or 25% chance of getting heads 2 times in a row, right? So we talked about this a little bit with the wheel. I'm going to over explain this. I apologize for it, but I want to make sure you understand why we can do it this way. So, side note, just imagine we have flip the coin twice. We can get heads, heads, we can get heads, tails, we can get tails, heads, we can get tails, tails. Now, again, there's a 50% chance or a 1/2 probability of getting a heads the first time times a 1/2 probability of getting heads the second time. 1/2 times 1/2 gives us 1/4 overall. Same thing here. It's a 1/2 probability of getting heads the first time and a 1/2 probability of getting tails the second time, which means that's also 1/4. Now you can see that there's 4 outcomes. Each of these is going to have a 1/4 chance of happening because there's 4 outcomes and they're 4 equally likely outcomes. But another way of remembering it is because they're independent, right? One coin flip doesn't influence the next coin flip. You can essentially just multiply the probabilities together. That's the thing to remember here is that independent rule here still applies. So if there's a 60% chance of being a quiz on the first day, then there's also a 60% chance of there being a quiz on the second day. So 2 consecutive days would be 0.6 times 0.6, which is 0.36 probability. So that's what we're trying to remember here. So moral of the story basically is you could take the odds of the events and multiply them together. So multiply, right? Now, again, if you want to keep this going, if I ask, hey, what's the probability of getting heads 3 in a row? Well, you don't have to think of all the outcomes and say, oh, how many outcomes are there? You can just say, hey, it's a 1/2 times a 1/2 times a 1/2 probability, which is a 1/8 probability overall. So it's easier if you can remember, hey, they're independent events. So let me just take their odds of happening, multiply them all together. That's the trick here. Okay. All right. Number 3. In a large county in central Pennsylvania, 44% of all registered voters are Democrats and 47% are Republicans. What is the probability a randomly selected voter is not affiliated with either the Democratic or Republican Party? So we have 44% for Democrat. We have 47% for Republican. If you add that together, that is 91% overall. So that must mean because, 1 minus 0.91 leaves us 0.09 or 9%, right? There's 9% that's unaccounted for. Those unaccounted for people are obviously not associated with either the Democratic or Republican Party. It's 9% that are something else, some other party or independent or something like that. So simple answer here, 9%. Or 0.9, or sorry, 0.09 rather. Either one of those technically correct. If probability of A is 0.39 and probability of B is 0.48 and probability of A and B is 0.21, what is the probability of A or B? So this is asking basically if you remember the formula for this. It's very simple if you do. The probability of A or B equals probability of A plus probability of B minus probability of A and B, which in this case, we have 0.39 for probability of A, 0.48 for probability of B, and then we have 0.21 for the A and B. So just simply add these together. And then obviously subtract the 0.21 and you have your answer, which is, I don't have my calculator on me, so I have to do this in my head, which is kind of early in the morning. I don't want to do that, but we'll do it anyway. Let's see. 0.87 minus 21 is 66. Okay, I might have done this wrong, but I'm going to go 0.66. All right, let's look at the next one. Two events A and B are said to be mutually exclusive if mutually exclusive if they cannot happen together. They cannot happen together. All right, give me 1 second. I'm gonna go get my calculator. All right, cool. I was just making sure that 0.66 was right. It is. I didn't want to have that wrong on here when I posted it later. Yeah, so two events A and B are said to be mutually exclusive if they cannot happen together. Plain and simple, nothing more to it. Remember the definition of mutually exclusive. In one large city, 80% of all households own a dog, 70% own a cat, and 55% own both. Find the following conditional probabilities. Now remember the conditional probability formula. If you have probability of D given C, which is what this says, right? D given C. And this one down here is C given D, so it's a little bit different. The conditional probability formula would be the and on top, so probability of dog and cat over the probability of the second part, the given part. So in this one would be probability of cat. On the one below it, it's still gonna be cat and dog on the top, probability of cat and dog, which is the same as dog and cat. Over, again, the second part, probability of dog. So remembering the formula here is gonna help. Now, let me fix this a little bit because it's a little bit, there you go. Dog and cat. Well, remember the probability of having a dog and a cat is 55%. So you can put 55, you can put 0.55. It's not gonna really make a difference. 0.55 is the probability of owning a dog and a cat over the probability of owning a cat, which was, as you can see up there, 70%, so 0.7. So 0.55 divided by 0.7 is 0.79, 0.79, if we kind of round it a little bit, 0.79. Now, for the cat given dog, we have the probability of cat and dog, which is the same thing again, cat and dog, same as dog and cat. That's both, right? That's cat and dog is both cat and dog. So it's still 0.55 over, but this time it's probability of a dog. Someone has a dog, which was 80%, 0.8. So now we're taking 0.55 divided by 0.8. We get 0.69. And there you have it. Those are your values. So remember the formula. Remember specifically the denominator portion as well, because obviously that's the make or break here. So you could very easily get these backwards if you don't remember that. So try to remember the denominator part and where it goes, what it is. All right, next question. A survey, sorry, was completed by 400 students, which is summarized in the two-way table below. Find the following probabilities round to the nearest two decimals and determine if the two events are independent. The notation for the event is in parentheses in the table. So this is pretty much the same thing as what we did in the skill check. So if you've done your skill check, you'll recognize this. You'll be familiar with this. All right. So this first one says probably someone has allergies given it's spring. So remember the formula. Probability of allergies given it's spring is allergies and spring over spring. Because remember the second part is the denominator. So let's look for these numbers. Allergies and spring. So allergies, yes. Spring, yes. That is 50, right? There are 50 that have allergies and like spring the most. Over, now this is again important, over spring. So we're looking for the total of spring. So spring total is 80. So it's 50 out of 80, which comes out to 0.63. Oops. 69. There you go. All right. Now allergies given not spring. So again, what we need is probably allergies and not spring over, again, the denominator part, not spring. This could be a little bit trickier. So allergies and not spring. So again, you have allergies, yes, and then not spring. Okay, that's gonna be 70, 60, and 15, right? They have allergies and they chose something that's not spring. 70, 60, and 15. So 70 plus 60 plus 15 over total for not spring. So our totals for not spring are these 120, 150, and 50. 120, 150, and 50. So all those numbers, if you add them up, let's see what we get. 70 plus 60 plus 15. Is 145, of course. And then 120 plus 150 plus 50 is going to be, let's see, 200. So 320. So we have 145 out of 320, which simplifies to 0.45, 0.45. All right, there we go. Now, because these numbers do not equal each other, these ones are not independent. Remember, these values would be equal to each other. Probably spring and probably get not spring. If they're equal, they would be independent. They're not equal, so they're not independent. All right, now winter given allergies. So winter given allergies, my probability of winter and allergies over probability of allergies. All right. Gotta get a new one of these. So winter and allergies. Let's clear this up real quick. Winter and allergies. Allergies, yes. Winter, yes. That's 15. Over allergies. Total for allergies is 195, as you can see there. 195. So 15 out of 195. Which is 0.08. And then winter given not allergies, so probability, again, we need both. Winter and no allergies over probability of, again, the denominator part, no allergies. So winter and no allergies. Winter, no allergies, that's 35. Out of the total of no allergies, so if you see the total for no allergies, total for no allergies is 205. So 35 out of 205 is 0.17. And again, these are not equal, so therefore they are not independent. All right, fast food restaurants sell food and beverages. Yesterday, 300 customers came into a fast food restaurant during lunchtime. Of the 300 customers, 240 ordered food, 210 ordered a beverage, and 200 ordered both. Suppose one of these customers is randomly selected. Put all answers in decimals from rounded to 2 decimal places. All right. So Venn diagram. You'll have to do this part on paper when you do the quiz, but here we go. We're gonna have food, we're gonna have drinks. Now we have 200 that ordered both. So 200 goes right in here. We're gonna have 240 added food, so we already have 200, so this would be 40. 210 ordered beverage, we already have 200, so this would be 10. And then customers altogether. So this is 250 so far, but there are 300 in total, so that would mean that there must be 50 more here. 50 other customers that, I don't know, got something else. Souvenir, I don't know. All right, so find probability, no food and no beverage. So probably someone got none of them, right? Well, we already know that that was 50 people out of 300. So 50 people out of 300, which comes out to 0.17. If you round it, that's probably that person ordered food or a beverage. So if they ordered food or a beverage, again, you can see the totals in the Venn diagram. That was 250. Remember, it's the 40, the 200, and the 10 added together. It's food or beverage, and or both. That's 250 out of 300, which is going to be the opposite. So 0.83. And if you know the person ordered food, what's the probability that they ordered a beverage? So this is the probability someone ordered a beverage given that they ordered food. Or I guess I put D for drink, didn't I? So I'll use D. Probably someone ordered a drink given that they already ordered food. So drink and food, remember, was 200 people. Drink and food over probability of food. So there was 200 people that ordered both, and people that ordered food was 240, because 200 plus 40, remember, is 240. So 200 out of 240, which comes out to 0.83 again. 0.8, oops, 83. So there we go. Doing well. All right, again, watch these back if you need to. I'm trying to hustle this out. So, all right, 2 more questions. Some very long questions, but we can do it. A census of students at a very large high school was taken, and each was asked their grade level and which location they ate lunch during, or every day during one of the 3 lunch periods. The results are summarized in the table. Suppose we choose a student at random from these 2,540 students. So probability we choose a freshman. So this is not a conditional probability, so it's going to be out of our total of 2,540. So we just need to know how many freshmen were there out of 2,540. 625. So 625 out of 2,540. Which is 0.25. Simple enough, makes sense. Sophomore and small cafeteria. Again, this is not conditional, so it's going to be out of 2,540 again. But it's a sophomore and they're in the small cafeteria. Sophomore, small cafeteria, that's 275. 275 out of 2,540. Which is about 11%, 0.11. Junior or large cafeteria. This one's going to be a little more interesting because you'd have to use your equation here. Junior or large cafeteria. So junior, we have 635 of them. Large cafeteria, we have 1085. Let's subtract the overlap, junior and large cafeteria, which is 375. And we end up with, let's see here, 635 plus 1085 minus 375, 1345 out of, don't forget, out of 2,540, which ultimately comes down to about 53, 0.53. So what I'm doing here, if you didn't catch on, was probability of junior plus probability of large cafeteria minus probability of both junior and large cafeteria. Because that's the formula you use if you want to find or, right? Probability of junior or large cafeteria. You use that A plus B minus the A and B, right? The same formula we used back in number 4. Doesn't have to be done that way, but that's the way I feel like would be best if you want to, if you want to be right. You can, there's other ways to figure it out, but that's the way I've done it the most. So, all right, the last one is a conditional probability. So this one's not out of 2540 like the rest of these were. This one's going to be out of something else. So senior given a student center. So we want the probability, we want senior and student center over probability of just student center, right? Because the second part given is the denominator. So senior and student center was 280. Out of our total for student center total, which you can see here is 595. So 280 out of 595, which is 0.47. All right. That does it for that one. Now let's wrap up with number 10. An airline claims that there is 0.3 probability a randomly selected business traveler will check baggage. An agent at the check-in counter records whether each business traveler checks baggage. Explain what probability 0.3 means in this setting. Well, it simply means that there's a 30% chance a randomly selected business traveler will check their bag. That's all it is. It just translates to a 30% chance or 30% probability. Does this probability say that if 100 business travelers are selected at random, exactly 30 of them will check baggage? Keyword here exactly. The answer here is no. Because of sampling variability, it could be slightly up higher or lower. I don't know how I wanted to write this, but higher or lower than 30. Right? Because I mean, sometimes it might just be 28 out of 100. It could be 33 out of 100. It's not going to be 30 out of 100 every single time, right? Sampling variability will change. It will average out to 30 out of 100, but each sample themselves might be different. You might get, like I said, 29 out of 100, 28 out of 100, 31 out of 100. It's not always going to be 30 out of 100. All right, lots of reading here. An agent observed 7 out of 12 business travelers who checked baggage. She would like to know if this outcome provides convincing evidence that greater than 30% of business travelers check baggage. To help answer this question, we want to perform a simulation to estimate the probability that 6 or more out of the 12 business travelers, I think it's supposed to be 7 or more, describe how to use a random number generator to perform one repetition of the simulation. So because it's a 30% probability, I would use the numbers 1 to 10. 1, 2, and 3 would represent somebody checking the baggage. And then 4, 5, 6, 7, 8, 9, and I guess 10 or 0 maybe. We can make it 10. Represent somebody not checking their baggage, right? So set number generator to 1 through 10. Let 1 2, and 3 represent someone checking bags. Let 4, 5, 6, 7, 8, 9, 10 represent someone not checking their bag. And then pull 12 numbers and count how many 1, 2, or 3s. All right. So yeah, I would pull 12 numbers and see how many of them were a 1, 2, or a 3, because those represent people that checked their bags, and all the other ones represented people who didn't check their bags. So if I got a 1, 2 2s, and a 3, that'd be 4 people, right, out of 12, which is not 7 out of 12, right? That's kind of the idea there. So to determine if these data provide convincing evidence that more than 30% of business travelers checked baggage, 100 simulated samples of 12 business travelers were selected, assuming that 30% checked baggage. The dot plot shows the number of business travelers in each simulation and simulated samples that checked baggage. Use the results of the simulation to estimate the probability that 7 or more of the 12 randomly selected business travelers checked baggage. All right. So basically, this chart here represents 100 of what we just talked about in part C. Like this dot here, for example, means that in somebody did pulled 12 numbers from 1 to 10, right? They pulled 12 random numbers from 1 to 10, and only one of those numbers was a 1, 2, or a 3. So, that sample could have been like a 7, a 6, a 4, a 9, 10, a 3. I'm just making stuff up here. It only goes to 10, right? So 8, 5, 4. How many have I done so far? That's 8, 9, 6, 5, and 8 again, right? It could have been like they pulled 12 numbers from 1 to 10, and of the 12 numbers that you see, only one of them was a 1, 2, or a 3, which means only one person checked baggage. So that's what that sample could have looked like as an example, right? One that's up here, right, would have been something that had like 2 digits between 1, 2, and 3, right? Et cetera, et cetera. This one down here that had 7 would have been one of these samples where there 7 of the numbers were a 1, 2, or a 3. So I'm missing one, but that's kind of the idea though. 7 of the numbers. So it could have been something like that. I think that's 8 numbers, but anyway, you get the idea. That would have been like this sample then. You pull 10 random numbers and you count how many of them are 1, 2s, and 3s. And then you record it on that dot plot and you do it 100 times. So that's what those are. So they've done it 100 times. And now look at how many of them had 7 or more out of 12. Well, 7 or more out of 12, there's 3 out of 100. That's all we're looking for. So 3 out of 100, or about 3% chance that 7 or more people would check bags. So there's a 3% chance that these travelers would check their bags if the probability really is 30%. So it's not a very high percentage. All right, based on the actual result of 7 business travelers that checked baggage, and your answers to part D. Is there convincing evidence that more than this should be 30% of travelers checked baggage? Explain your reasoning. I would say yes, because the probability of 7 or more checking bags is 3%, which again is lower than the 5% threshold. Remember, if it's less than 5%, it's convincing evidence. If it's greater than 5%, it's not. Okay. So you have to remember that. It's under the 5%, it's less than 5%. So it's convincing evidence that it's really larger than 30%. It's not exactly 30% of business travelers. We're convinced that, well, it's probably more than 30% of business travelers who check their baggage. So is there convincing evidence that more than 30%? Yes. Because the probability of 7 or more is very unlikely to happen. If it was 30%, it's very possible that that real percentage is larger than 30%. I want to see if there's anything else I want to add to this. I think I'll just leave it at that. Yeah, for now. I'll post this on. I'll see you guys in class. If you have any questions, just let me know. But for now, good luck. Yeah, and I'll see you for the quiz. Bye for now.